Hello, ladies and gentlemen. Today we're going to be talking about a new type of question. Now, this type of question is a launched at an angle question, where before we were working with horizontally launched projectiles, or projectiles that are fired exactly to the side. Today we're going to be dealing with projectiles that are fired upwards, up at an angle. Now, this is our capstone type of question. This combines everything that we've talked about so far this year. In order to answer these type of questions, we'll have to know about vectors and how to add and resolve them. In order to answer this question, we'll have to know about all of the motion equations and all of the tips and tricks we picked up along the way with motion. In particular, this is going to be very similar to vertically launched projectiles, or projectiles that are fired straight up into the air and back down, where we'll be using our tricks of breaking it up into parts, also paying attention to things like negatives and positives, or when things are going in opposite directions, and using, of course, our zero speed at the top of the arc is very important. We will also be using everything that we've learned from horizontally launched projectiles, in particular, organizing things in our if-dat chart, knowing what's in X, knowing what's in Y, and how to deal with those two directions at the same time. So, like I said, this combines everything. Now, to start off with, let's look at an example question. So here we have a cannon that's fired 30 meters per second at a 40-degree angle. So we're taking a cannon, we're firing at an angle, and we're having it land actually on the same place that's fired at, the same plane, so on the ground basically. Now, the first step we have to do to answer this question is to resolve our vector. So we have a 30 meters per second vector at a 40-degree angle. We have to break it down into its X and Y components. We have to figure out how much of the speed is horizontal, which is going to go on our X, and how much of our speed is vertical, which is going to go into our Y. So to figure out what the X component is, we're going to be, let me just get my laser pointer, figure out what this component is, we're going to have to use cosine, adjacent over hypotenuse, solving for X. So solving for X, we get 22.98 meters per second. So that is the speed in the X direction at the start of this problem. Now for the vertical direction or the Y direction, we're going to be using sine. Again, solving for Y, we get 19.28 meters per second. These will be our initial speeds in the X and the Y, because these are the speeds that it's fired at. This is why we resolve vectors. This problem would be way too difficult to figure out if we kept things at an angle, but by breaking it down into its two parts, we're able to simplify the problem and work with just an XY chart. Now over here, I have pretty much everything I need drawing-wise for this question. I have that same that same triangle that we worked with before with its two sides labeled. Here's a little diagram of the image. We're firing out of a cannon and we're landing at the same level that the cannon was fired at. Our goal for this question is to figure out how far it traveled in the X direction. So it went from here and it landed over here. We're trying to figure out what that distance is. And to start off, I'm going to be using our XY chart. So we've learned this 22.98 meters per second. And that's just going to go in the X, in the VI for the X. Our acceleration, the X, is the same as it always is going to be. It is 0. There's no change in speed in the X. There's no rockets attached to the cannonball, no parachute. Because we have no change in speed, it will stay 22.98 meters per second the entire way. The initial and the final are the same. Now, this is where it changes from our horizontally launched projectiles. Before, when we fired exactly to the side, we had no speed in the Y direction. But now we do. We have a velocity. It is 19.28 meters per second. Our acceleration in the Y is 9.81 meters per second squared. Now, you'll notice that I put a negative there. The reason why I put a negative is because I want to remind myself that there are directions involved in the Y dimension. Where X is always moving to the right, Y goes up and down. So I have to be conscientious about what direction things are. Now I put negative under 9.81 because it's going down, while our 19.28 meters per second is going up. That does not mean I'm going to actually put negative every single time I see 9.81. I'm still going to think about when I need negatives or not, but that negative is just there to remind me to be careful. As I said, the distance is what we're looking for. And right away, this does not look like we have enough information. Sorry about that little pop-up. We do not have enough information to solve the problem, but we do. Before we actually get to the main problem, I'm going to solve another one, which is to find the max height. And this is often a good first step in order to solve a problem. Figure out how high into the air from the ground it went to. Now we're talking about how high, so we're talking about the y direction. And I'm going to use VF squared is equal to VI squared plus 2AD. Now this is going to be very similar to a vertically launched projectile question. I can't answer this question through the entire path of the motion. Instead, I have to use half of the motion. In this case, I'm going to use the first half of the motion. Plugging this in, I have my initial velocity of 19.28, my acceleration of negative 9.81, and you'll notice that I have 0 for the final velocity because that is the speed the ball is going at the very top in the y direction. Yes, it's still moving at the very top, but all of that motion's in the x, none of it's in the y. So just like a vertically launched projectile question, at the top of the arc, our speed in the y is going to be 0. Solving for distance, I get 18.9 meters. And that is, again, the height that it ends up traveling. Now, I'm going to put that in right here. Now, one thing to note about our final speed in the y. We actually know what our overall final speed is in the y, the speed that it lands at. And that's another trick from our vertically launched projectiles. This is a mirror image. The start is the same as the end, just in the opposite direction. So if it's fired upwards at 19.28 meters per second, it also lands at 19.28 meters per second. So our final and our initial speeds are actually the same, just in opposite directions. One's going up, one's going down. So I'd probably, if I did write it in here, I'd probably want to include a negative. Now, let's figure out the time it takes to get there, to that halfway point. Now, there's a lot of choices in solving this problem. You could actually just go ahead and solve for the entire motion of the problem, or you can do what I'm doing, which is just solving for half of it and then eventually doubling it. Choice is yours. You can basically use any formula at this point, as long as it has acceleration in it, and you'll get the right answer. Now, looking at our formula here, I'm going to use El Grande. I think it's the easiest formula to use. And rather than using the first half of the motion, I'm going to use the second half of the motion. And the reason why I'm doing that is so I can make my initial velocity 0. If I used 19.28 meters per second in the initial velocity, and I chose negative 9.81 because it's going the opposite direction, I would get the same answer as I would get right here. But what I would have to deal with is time in two places. I would have to use the quadratic formula to solve for this, and I don't want to do that. So to avoid that, I'm just going to use the second half of the motion. I get the same exact answer, but it's with much less work. So the other thing is you'll notice I kept both positive. That's because the 18.9 meters in the second half is going down, and the 9.81 in the second half is going down. They're in the same direction, so I don't need to put any negatives. Solving for time, I get a time of 1.96 seconds. If I double that time, I get 3.92 seconds. So this is my total time. This is the half time. Now, in order to find the distance in the x direction, it's the same as the horizontally launched projectile. I have the time, we have the speed that it's traveling at, and nothing is different here because our acceleration is still 0, nothing's changing. And if I solve the answer, I get 90.2 meters. So this was fired, it went up, and went a total of 90.2 meters. These type of questions are tough when you first start because it seems like there's so much that you have to do. But in the end, as long as you keep whittling away, as long as you keep trying to figure out different things in the y and x direction, fill in these boxes, you can arrive at the answer. It just may take a couple of steps to get there. The nice thing about this is if you're careful, you can use almost any equation, many different ways to solving this problem. At the very beginning, you could have found the time by knowing that it's 19.28 seconds here and it's negative 19.28 seconds here, and using A is equal to delta V over T to find time. So you could have just skipped like all of this to jump right to the answer. There's different choices for you. The reason why I picked this particular path is just so you can see finding each part. We can figure out how to find the max height. We can figure out the half time. We can figure out the total distance. Just little tricks that I'm trying to give you and used to. It doesn't mean you have to follow the exact path that I did. Just make sure you're paying attention to direction, positive and negatives. Make sure that you're only plugging in X's or only plugging in Y's, and take your time with it, and we can arrive at the answer. When we come back into class, we're just going to be taking a day to practice this. Because there's so much going on, it takes time. But in the end, we've learned how to do every single thing in this problem already. This is just a cumulative type of question that covers everything we've talked about so far. I hope you all have a wonderful day.